new phase space complexity of old globular clusters. So please go ahead, Annalisa.
Thank you very much. I hope you can hear me.
Yes, very well.
Great. Well, thanks a lot for allowing me to be here in virtual form and for setting up such a rich program. So thank you very much for this to the scientific organizing committee.
Sorry, Annalisa, sorry I
yes?
interrupt you. You can share your webcam for a few seconds and then
sure, yes.
turn it off because people
I'll say hi.
them.
Yeah. I hope it works. It's finding my webcam at the moment, so give it a moment of patience. Still looking for it.
Because we need it later
yes.
for a group photo.
Of course, yes. I'm doing my best. I'm still looking for my webcam that is clearly there on my computer, but it's still looking for it. So let me try again.
And if it is not possible, then we can do it later, maybe.
Sure. Just do one final shot, and we'll see. Otherwise, I'll try again. No.
Okay.
Or at least it takes
so
a
we
little
can
bit.
continue then. Yeah.
Let me see. Wait a moment. Maybe I'm almost there. It just takes a little while.
Okay.
Can you see me now?
Yes, I can see. Yeah. Hello.
Hello.
Okay.
Okay.
So we can continue. If any problem in the net, then we can turn it off. So.
Okay. So I'll leave it there for the moment,
yes.
and then if otherwise, I'll switch it off. Okay. So as I was saying, thank you very much for having me, and thank you for organizing and putting together such a nice, rich scientific program and juggling all the time differences for the speaker. So I'll continue on the same topic that Pavel opened up in the session, which is related to the dynamics of collisional system, and in particular reference to all the globular cluster. So older system compared to the one that Pavel introduced just now. And in particular, I'm a person that lives at the interface between astronomy and applied mathematics, as I am based also in Edinburgh in this kind of arrangement. So this topic is going to be a bit more on the theory side, and with emphasis on what I would call phase space complexity, which is essentially trying to tease out the information related to the phase space, which means the configuration space and the velocity space considered all together. So I'm comfortable in opening up this talk with a powerful statement that I don't think it's an overstatement, in the sense that I genuinely believe that we are at the stage in which there's going to be a renaissance, a new golden age for the study of star cluster dynamics. And this is really determined by the alignment of three transformative shifts in our studies of our own galaxy, mostly thanks to three different dimensions, as I said. So the first sort of dimension of interest here is observational. As I said, I'm a theorist, but I recognize that much of the driver is really coming from the observational perspective here. And this means really, from the local universe perspective, Gaia. And I know that apart from the references that Pavel just made in the previous talk, but also you heard from Holger Baumgart, who was really giving you an overview on what we have learned from the current data release 2 of Gaia for the purpose of globular cluster science. So a lot has been done, but there is a lot that will come through the next data releases. And in particular, my angle here of interest is the fact that we can combine essentially the information from the proper motion derived from Gaia, that is really opening up the phase space in the outer region of many classical galactic globular cluster, with respect to Hubble Space Telescope, long baseline studies that have been completed over maybe 15 years now, and that are delivering essentially the scientific content in just the last few years for specific nearby globular cluster. This is also supplemented by current available and forthcoming spectroscopic information that is supplementing essentially the kinematics on the line of sight that is really complementary with respect to the one in the plane of the sky that we can achieve from the proper motion perspective. And there are a number of facilities that are coming online in the next few years, hopefully, that will be really enriching this landscape, in addition to the Gaia ESO survey that is already designed to really be complementary to the Gaia existing astrometric satellite. So this is really complemented again by additional information, not just based on the local universe perspective, but also on the early universe one. This to me was a surprise about 2 years ago or so, that people essentially started discovering the existence of very compact star-forming region analyzed primarily in the Hubble frontier field. So I put there a few references for you to orient yourself. This is a plot taken from Bowens et al. 2017, but there are other people, especially Vanzella and collaborators, that have been very active in the last 3 years or so in identifying strongly magnified sources. So all these dots that you see on this plane are still depending on heavy magnification, and therefore all the limitation on this kind of discovery is not as easy as for the local universe type of sources. So there is a lot of uncertainties, but nonetheless is an indication that we are moving progressively in the direction of populating a portion of this mass size plane that seems to be consistent with what we would like to call eventually a protoglobular cluster. And note that this is really early time, in the sense that these are sources identified as redshift 6 to 8. So there is a lot of expectation from the point of view of the community of what James Webb and the sort of complementary extremely large telescope for the spectroscopy might be delivering. And essentially this is really the hope, to try to see the star formation of globular cluster in action at some point when those facilities will be truly available to us. There is a second layer here, which is the computational revolution that is ongoing. And this is again twofold. So our community had a long-term goal, and again, Pavel made reference to it, and Jeremy Webb, as well as Holger, presented you a number of results, and I know that you have a very strong expertise locally on this. But nonetheless, it's really the effort of a few people that offered us the technology, in the sense of the right computer code and hardware sort of management, in order to perform these solutions that are, as Douglas Eggy, who is here with me, thankfully in Edinburgh, would call a honest and-body simulation. So no cheating in that sense, really integration of the equation of motion for a million body particle throughout the full lifetime of a globular cluster in this case, which is 12 to 13 giga-years. So we now have a series of landmark studies in which there is really the delivery of this gravitational million body scale quality model available. These are still very expensive simulations, some of you know, but nonetheless, it was a really a breakthrough for our smaller community. This is supplemented from the perspective of the larger community that is investigating the cosmological context. And indeed, we are not there yet of having a cosmological box that is delivering the right, as they call it, subgrid physics, as well as mass and spatial resolution, in order to really resolve exactly the formation of a globular cluster in action at early redshift. But nonetheless, there is this tendency in the community in really trying to come together. And there has been recent progress in the last few years. I put a few references there, but there is a lot of activity now, especially really that people that are normally interested in cosmological boxes are now paying attention to smaller and smaller scale. This is also having a theoretical implication. In particular, people are been starting to ask what is the role of these small star-forming sources that, as I showed you, are now becoming a reality even in observation. What is their role in the epoch of reionization? And people have been studying this in the past, and as I said, there is a renaissance of interest from the point of the theoretical assessment of what is their role in the energy budget at the reionization epoch. So as I said, it's a very lively development for the extended community. But there is an additional layer, which is probably the one of most interest to me, which is related to the conceptual evolution here. We normally have been trained in textbook to assume that globular clusters are beautiful yet relatively simple sort of phase space laboratories. And the assumption normally is that these are spherically symmetric, isotropic, non-rotating configuration, where the stars are randomly sort of oriented. And of course, there is already a rich paradigm there to explore in terms of the classical understanding of the evolution of this system as self-gravitating system with a negative heat capacity. But nonetheless, now there is, I think, the possibility of opening up the new dimension related to this kinematic richness that we can now really measure. And here I'm just giving you two references to early measurement of the degree of internal rotation of the system, as well as the possibility of separating component of the velocity dispersion in the tangential and radial one that gives you the possibility of measuring what we call velocity anisotropy in this context. So a preferential orientation of the orbital distribution either in the radial direction or the tangential one. Just years ago, when I started my PhD, this was almost a science fiction type of constraint. And fortunately, now we're at the stage, thanks to Gaia as well, that is really allowing us to have this kind of phase space information in the outer region of many classical globulars. We can really use this information to test more sophisticated dynamical models and ask ourselves more interesting dynamical questions even. So in addition to this, there is this layer of complexity that is sometimes called chemodynamics. So that the attempt or the importance to try to link the dynamical constraint with respect to the one on stellar population and chemical sort of dimension. So you might have heard the issue related to the multiple stellar population phenomenon, not really quite related to the kind of different population that Pavel was introducing just now, but not that different to some degree, in the sense that there is still a lot of uncertainty in the community in trying to pinpoint the physical origin of this multiple stellar population phenomenon that is now almost a jargon to refer to the fact that there has been sort of ubiquitous evidence of particular enrichment in the light element variation that is really emerging in all galactic globular cluster, as well as tentatively sort of presented as evidence also in younger massive system. But this, as I said, is a very much ongoing field of research, and there is no consensus yet. And here I think that my angle of interest is particularly related to the kinematics of these different populations. And I'm presenting you here two examples of how can you relate, for example, the degree of anisotropy to different population, and even more importantly, the degree of rotation with respect to the different population. This is why I was asking Pavel if he had any constraint on the kinematics of their own case of different population in the Orion Nebula cluster. An additional layer of interest in all this is a very sort of fashionable topic nowadays, which is the black hole dynamics inside dense stellar system. So now we are planning, we'll definitely into the LIGO era, and there is a lot of attention on trying to generate the right stellar mass black hole, and ideally binaries of those that are responsible for the event that the LIGO is progressively recording. And then there is the sort of elephant in the room, which is still the very unsatisfactory piece of evidence on the intermediate mass black hole that several of us are expecting to see at the center of classical globular cluster, but for which there is no consensus at all yet. Another sort of very active area of research in this context, and where I think that the sort of attention to the kinematic richness of the star cluster themselves can be very helpful in enriching our understanding of the black hole or few body dynamics in there. And the final layer of interest is related to what Jeremy Webb introduced you yesterday, which is the role of the tidal interaction with respect to perturbation experienced by the globular cluster throughout their lifetime, and the fact that they tend to generate streams, and the fact that you can relate those streams to a number of hot topics, for example, the characterization of the properties of the galactic halo, as well as the assembly history in there. So this is also an area in which, after the physical discovery and characterization, for example, of Palomar 5 here on the left, we also received a major burst from Gaia type of constraint. And one recent discovery was the very impressive long stream of the classical Omega Centauri that has been highlighted from DR2 studies. So all this, sorry for the long introduction, but to motivate, I think that there is a need to explore the fundamental implication of this that is revealing to us, and the issue of all star cluster in the studies landscape. And take on this is related to
sorry, Annalisa. We have a little bit noise with your voice, so I think if you turn off your webcam, maybe now
maybe
it's better. Yeah, better.
Better? Okay.
Yeah.
Thank you. Sorry about this. So goal number one is to really try to understand primordial and evolutionary features, because we know that collisional star systems are lively objects, and they are really experiencing 13 gigayears of evolution in phase space, and this is really changing the way in which dynamics and observables are revealing to us, compared to collisionless system, in which such sort of evolutionary component is much less important. So there is a lot to be learned about the role of angular momentum and isotropy and interplanes. So this has been explored in the classical understanding, but I think that there is room for new discovery to be made here. And this kind of classical sort of understanding is also useful to try to fill the gap between what we normally see as the end of the star formation sort of regime of understanding in a cluster environment, much along what Paolo was describing, with respect to the series of classical studies that are very much in an idealized settings that we normally perform either on theory or classical M-body simulation, where there is really a major sort of distinction between the messy state that is predicted at the end of this cluster star formation evolution, and then what we normally do to initialize our long-term type of simulation. So I think that there is an angle to try to improve and fill in this gap. And the third sort of motivation for doing so is to try to prepare the ground in terms of really solid understanding of this classical physical theory before entering any sort of attempt to characterize more complex phenomena. And those may be this multiple population phenomenon, the presence of the MBH, or even this kind of tantalizing possibility of having any signature of dark matter in the non-baryonic sense. On small scale, there is a topic of growing interest in a cosmological context. So my angle here, and it's a bit of a bias, I rather first try to understand the classical physical ingredient, and then I feel ready to attack this more complex problem. And as I said, this is a very sort of powerful moment of this synergy between Gaia, LIGO, and the forthcoming James Webb Space Telescope. So because I know that we have limited time, I'll just focus on two old questions that are related to this concept of kinematic complexity, and in particular angular momentum, pressure, and anisotropy, for which we can report some recently. And then I'll close up this contribution with some speculation on what can be the role of these new results on all question in the modern context. So all question number one is, what are the stability properties of rotating anisotropic spheroidal equilibria? And I know that some of you in the audience are interested in this kind of theme, so this is why I decided to use this angle. So we attacked this problem from the perspective of a specific playground of models that you see described here. We didn't invent them. De Jong in 1987 presented this. And don't be scared about this formalism. It's just a distribution function that is a function of the single star energy here and the modulus of the angular momentum here. and this is just a series of Heaviside function with specific properties. But the point is that these are particularly well-behaved equilibria because they have the same structure in the density distribution. These are all Plummer spheres, essentially, very simple classical model. And they have a very well-behaved kinematics, and in particular, this beta profile that you see defined as essentially the ratio between the tangential component and the radial one is a very nice analytic function that just depends on the radius, the spherical radius here. These are all spherically symmetric configuration. And then depend just on a primary parameter here, this Q, that you should read as isotropic in the case in which is 0, because beta would be all 0. When it's positive is radial bias, so excess of radial orbit, and when it's negative is an excess of tangential one. So there is also a limiting, particularly interesting case that corresponds to Q tendent to minus infinity, and that is sometimes called Einstein sphere, because the man himself was studying this kind of equilibrium for different reasons at the time. And you can also explore the radial regime and relate this kind of series of models into even more radially sort of biased configuration that still preserve some proximity to this and will become radial orbit instability unstable. And I'll elaborate on this in a moment. So keep in mind that these are, as I said, are anisotropic spherically symmetric configuration. And what we did also, and you can plot out just for sort of visual understanding what is the shape of the beta profile as a function of radius, as well as the velocity dispersion profile as a function of radius. And you see that these are very different depending on the level of Q, the level of anisotropy, and the flavor of it that you're considering. So we also did an additional trick in the sense that we wanted to study also the role of angular momentum. And Donald Linden-Bell 50 years ago already presented this sort of solution for introducing angular momentum in a originally non-rotating system, just with the sort of trick of flipping around a fraction of the particle. If you consider a model as a discrete collection of particles with different orbits, essentially you can achieve this by sampling the distribution function that I described just before. And by doing this reorientation of the direction of motion of those orbits, you're essentially introducing angular momentum naturally. And mathematically, if you want to just explain this kind of trick, it's just a way to introduce an odd component to the distribution function that you see here with respect to a parameter alpha that is running between 0 and 1, where 0 corresponds to the case of no rotation at all, you're not flipping any particle, up to 1 in which you're flipping all the particles that are available to you. So you're introducing the full odd component of the angular available for that given density distribution. And the density distribution itself doesn't change at all, so it's still a Plummer. So why we did all this? Because we wanted to explore the stability of this slightly strange but yet very helpful type of sphere that are now anisotropic and rotating. So keep in mind the meaning of those Q and those alpha here. And what we were measuring here that you see plotted is the growth rate of unstable modes. So there is an indication that these configurations, these equilibria, are not all stable necessarily, where you see this cyan light blue part of the surface means that these are either very slow growing mode or consistent with stability. Where you see this orange part of the surface growing, this is a non-zero growth rate, this eta here. And if you're familiar with the sort of classical result on classical radial orbit instability, these corresponds to just the line of alpha equals 0 here, this sort of classical non-rotating regime. Positive Q corresponds to radial bias, as I said, negative Q tangential one. And the classical result that if you are essentially allowing too many radial orbits in the system, that will make it prone to create a cigar at the center, which is the essence of the classic radial orbit instability by Polychenko and Shukman in the 80s, is corresponding to this limiting case for Q greater than 2. What was a surprise to us was the realization that there is a series of new instability that you find naturally just by exploring this more extended parameter space. And this is really should be thought as an extension in the case of rotating system with respect to the limit of the classic orbit here, classic radial orbit instability here. But there is also, even more surprising to me at the time, the fact that there is a tendency for the system to become unstable in the tangentially anisotropic regime. So this is very difficult to try to pinpoint in the case of purely tangential, so non-rotating configuration. And as I said, there seems to be essentially little evidence for any unstable mode, or if there are there, with respect to the kind of methodology that we use to pinpoint this growth rate. These are very slowly growing modes, so a very small eta. But if you allow yourself some degree of rotation, so you move upward in this direction for a growing alpha towards the maximum alpha equal 1, there is clear evidence that these things will become, this sphere will become unstable, and there is again sort of an M2 mode developing in the central part. So this is a result that we achieved by the so-called matrix method, and I'm not going to say anything more about this because I'm running out of time already, with respect to the M-body case that we also tested against. So this was question number 1. Question number 2, more quickly, what is really the implication of kinematic complexity on the long-term perspective? So this was a result related to dynamical timescale. So there is a series of related questions on the long-term evolution driven by relaxation. So now just consider the case of the anisotropic sphere, not rotating at this stage. So the sort of de Jong style distribution function that I described. You use them to initialize classical M-body simulation, purely dynamical setup. This is the evolution of the core radius as a function of time. And progressively, you see that there is a contraction as expected that corresponds to the moment of core collapse. But the sort of interesting bit is the fact that the classical results corresponding to isotropic initial condition are the red one. But if you consider the tangentially anisotropic corresponding to these lines here, or the radially anisotropic one, there is a dependence on the moment of core collapse, depending on the degree of anisotropy that you allow the initial condition to have. So this was a surprise and an interesting result to me, because we never really considered this as relevant in terms of really making such a difference on the moment of core collapse. And this is really just another way to characterize this relationship that we identified in terms of the moment of core collapse and a global measure of anisotropy as the ratio between the ordered kinetic, the radial component of the kinetic energy tensor with respect to the perpendicular one that is a proxy for the tangential one. So again, just to give you a feeling for what happens next, is not just an interesting result on the fact that you're moving around the moment of core collapse, but also because you progressively generate erode the initial signature of primordial anisotropy that is available to you, for example, in the radially anisotropic positive case Q here, or all the negative one. But this is corresponding to the moment of core collapse rescale, and then you progressively generate evolutionary anisotropy as well, corresponding to this growing portion of those lines. Yes, Hossein, I'm seeing the time running after. So I'll skip a couple of those, and I'll just run through quickly on the implication in questions. So here is just to show you why is it interesting to still go back to these old problems in the context of new topics. And in particular, a series of questions that are related is, for example, what is the phase space structure of multiple stellar population cluster? Which we understand is on the fundamental of this kind of phase space complexity. We can relate this to the different population information. There are new results that are coming online progressively, and through Gaia we will know progressively more. Then what is the long-term evolution of the kinematics of those multiple populations with different interesting kinematics? And there are several purely dynamical questions related to this, and ask me questions if you're interested on it. What are the phase space properties related to, can we use this kind of phase space information to try to pinpoint the formation process to a better degree? And this is really complementary with respect to the early universe information that is progressively emerging to us. And the second sort of laundry list of information for this link between phase space complexity has to do with the black hole as anticipated. So what is predictable at this stage, what are the phase space structure of rotating anisotropic equilibria with a central black hole? This is another sort of classical topic, and people investigated mostly for nuclear star cluster more than classical globulars, but nonetheless some results are there, but we can do more than this, and then investigate the stability properties and their secular behavior as well. because there is a lot of unknown sort of component related to the role of angular momentum in particular. This is also related to a number of results that are available to the community, mostly from studies on the fluid dynamical side, more than the stellar dynamical one. And there is a nice legacy of results from the Japanese community that, for me, is really very much the guiding principle on how to attack this problem, even on the stellar dynamical side. But I won't say anything more about this, so ask in the question time if you're interested. And then there is the whole set of questions related to the collisional evolution, mass segregation, and how this will be impacted by the role of angular momentum and anisotropy. And we are studying some of these problems with people in Edinburgh. So also related to this, what is the impact of this phase-space richness on the formation processes that are known to the community for the formation of intermediate mass black hole through runaway collision, for example, or slower processes that have been recently identified in Monte Carlo models. And also then, how do you retain, how this is impacting the retention of stellar mass black hole, merger rate, and tidal disruption events, and all this sort of topical question of interest to the broader community, with implication for gravitational wave detection, as mentioned at the beginning. So I'll just leave you with my conclusion. I'll put everything up there one by one. Apologies if it's a little bit slow, but the bottom line really is that there is a lot to be investigated, and I think a lot to be learned even just by studying the classical physical ingredient. Thank you very much.
Thank you very much, Annalisa, for very nice talk. Okay, so any question? I should check if anyone raised their hand or not. Okay, seems Asya Yaqub is typing. And also Pavel Kurba is typing.
Sure, Pavel, go ahead.
Yes, please, Pavel.
Yes, hello. Can you hear me?
Yes.
Yeah.
Okay, good. Yeah, I'd just like to ask about the omega sen tidal tail. You showed the image, and I just wanted to know if you could. Do you think you might be able to show it again and just show Vega Centauris and what that structure looked like? Because it looked very bended, right? So it's just...
Yes. Yeah. So thank you. Very good eye. Let me find that slide if I manage. Here it is. So very good. I wasn't not involved in that study, but a collaborator of mine, Paolo Bianchini, was heavily involved. And he told me, and it's also written in the paper itself, that if you try to generate an M-body model that corresponds to a classical initial condition for omega sen, to try to reproduce this shape of the bended long stream that they identified, you fail. And the only way in which it was possible for them to use, this corresponds to those black dots called M-body particles in the legend here. The only way to reconstruct this kind of bended shape was to introduce a degree of rotation for the progenitor in their model. So as we know, Omega Centauri is rotating. I modeled this already pre-Gaia, and we are trying to put together a model now with consistency with Gaia kinematics. But it seems to be really key to allow this level of complexity of the kinematics in the progenitor in order to reconstruct the peculiar shape of the stream itself. So I was very pleased to see this, even just to read it, because I always had the sort of gut feeling that many features on the streams that people are identifying progressively studies for all sorts of reasons, as Jeremy explained, do really need to account for the role of the internal kinematics of the progenitor that is unfortunately hardly ever done.
Indeed, that's really fascinating. So did you by any chance maybe predict this with your calculations?
No, I never really, I'm slow, so I take problem one by one. So I never managed now to get to the stage of really characterizing the orbits and do what Andreas Cooper and Douglas were doing in this sort of classical settings for studying the overdensity and the implication of this. But even just in terms, I think, of almost back of the envelope kind of intuition, you really have different angular momentum attached to individual orbits that are the one that, for example, are potential escapers first and then will generate the members of the tail themselves. So this will naturally be asymmetric with respect to even just the case of a circular orbit, if you allow this rotation to be in place. So just on the basis of this was essentially my intuition for having something that is non-negligible. So there are a few other studies of people that were starting to consider this in the case of stream associated to dwarf galaxies, for example. So I can send you a couple of references about this. But I think that now it's just the beginning of this, well, possible opening up of the further detailed studies for the stream themselves, and possibly the possibility of having more accuracy in the description of the progenitor. So hopefully will come. And I'll do my best to do better, sort of more tailored theoretical models for doing this.
Yeah, many thanks.
Okay, thank you very much. And any more questions? We have 1 minute for more questions.
No problem.
Okay. So